So for today's class, we start by showing us how to read the IDF, intensity, duration, frequency curve. You can call it the IDF, you can call it the rainfall data, you can call it other precipitation data. There are many names you can call it. As I said, when it comes to infrastructure or water, in the water sector, there are words you can use interchangeably. So for today, for this IDF, you use it to design storm, which has to do with hydrology. So the most important input parameter or the parameters you're looking for, the output parameter you're looking for is the amount of rain. Because if you get the amount of rain, you multiply by catchments, you get your Q or flow or discharge or runoff. If you apply peak factor or peak runoff coefficient, you get your peak value, which you can now use to size your drain. Okay, remember the universal formula CIA. Okay, or A or Q equal to AV. I can't help emphasizing this. If you can capture that principle, if you can capture this universal formula that Q is equal to AV, then you are gone. It is fluid mechanics, thermodynamics, or hydraulics. Okay, which could also, if you split it down, to give you CIA, where A is your area. Okay, this area could mean your area of, to get your Q, it means that this area will be the area of catchment. Okay, but when you now get your Q, you now want to find your pipe size. The area becomes the cross section of the pipe. Area of catchment or pipe diameter. Okay, so that is that. So I just say, let me refresh our mind on that. Very, very important. So back to how to read this IDF curve. So here we discuss about 10 to 15 minutes. Remember, just have it that way. If you want to know why we use 10 to 15 minutes, you can Google it. I explained it last week. So 10 to 15 minutes. It cannot be more than that. So for now, let's say we use 10 minutes. So now, let's say I'm designing for normal drain. In the manual, I'll show us where you need to, where there's a guide on what to use. So let's say we are using a 2-year return period. What does 2-year return period mean? It means that what is the water rainfall that will happen every 2 years from a layman's perspective. So once I come to 10, worry, I'll read it off. And you can see it's giving me 140. Then for 1 year return period, it's giving me about 120. So you can see that as I'm going using a higher year return period, I'm increasing my factor of safety and the value is going higher. And as that value is going higher, that is how your drain size will become bigger. So you can see that for 10 years, this is what this student used. If I could quickly go back, where did I get? Okay, let me go to our platform. Let me see what he used. Okay, that's for JeffCon. Okay, let me just quickly see what he used, just to show you that sometimes this material is valuable because it has taken care of the labor or the energy you need to go. Let me pause this so that it doesn't become too big. So we are good to go. Okay, after the question, Engineer, you get everything, please. Let's continue. Let's continue. Okay, so can we all open the charts written rational method? Yes. So this is the exercise. So this is a little catchment you're going to design in this class. This is the rational method. So this is the catchment you are giving. So this could be, what do I call it? This could be a catch. This is a regular catch. It's like regular, but in real life, it will not be like this. It will be like complicated. Okay. So you can see this place is catchment A. Catchment A. Don't mind the piping, please. It's you that will draw the piping. So this is how the network will look. So what you have here is, this is a pipe. It connects to catchment B. catchment C comes in, catchment D, then finally it goes to the outfall. So this is the outfall. This is a river. Remember the diagram I showed us last time. So this is like there's a stream here now. So this is storm. We're doing storm now. Okay, we're doing storm. Let's start with storm. Next week we can do sewer, or we can do both if time will permit us today. So now we are assuming that this is a fixed boundary. When I mean fixed boundary, that means that water cannot flow out of these places. All the water will accumulate and then discharge here. All the water will accumulate and then discharge here. That's what it means. So what this means is that catchment A will empty into catchment B, catchment C will join them and empty into catchment D, catchment E will empty here, catchment F, then catchment G will come, and then back to catchment. So as the water is flowing downstream, of course, is peaking, is increasing in quantity, is increasing in sizes, and as expected, the pipe sizes will be increasing. Okay, so if you are given a question or a challenge like this, or a layout like this layout can come in any way. Okay, it is too simplified here, but in real life, it can come in form of, let's say this. Let's say this. Yeah, so this can be a catchment. It can come like this, and you're asked to design this. So what you do, you can see that if I know the elevation, the spot height, I can know that if water from this catchment is flowing towards this drain, and then if this one is flowing towards this drain, or this one is flowing towards this drain, then once I know that, then I can know which one will empty in where. So I can know whether this one is flowing down here, or whether this one is flowing down here. Okay, based on the elevation and the spot height. So once I'm able to do that, it makes my life easy, because then if I just want to calculate the drain, I'll know the area here, multiply by the precipitation, multiply by the peak runoff we discussed last week, which gives you the degree of paving. Then my answer will fall out. But just take it easy. Or you can come in form of this. If you look at this, you know that these catchments have divided themselves. Look at these road boundaries, already catchment boundaries. Look at it. So this is catchment 1, 2, or 2, 3, okay, 4, 5, 6, are you getting it? 7, and so on and so forth. So why I'm showing this is for you to just try to understand what we have here. So if you are given this, the first thing you do is develop a table. Remember what we did when we were doing water rectification. You develop a table like this, okay? This table like this, you look at the pipes, pipes A to H. Then they are starting from here, they are ending here. And this is their length. So automatically, the slope will now be the surveyor level or the spot height. Difference in the spot height divided by the length will give you the slope. So here, pipe A is starting from 2.1, 2.3 to 2.1. So the slope of this pipe will now be the change in height, assuming that this is the value from surveyor. It will be change in height minus the change in beginning of the pipe minus the spot height at the end of the pipe divided by the length of the pipe. So as we also discussed in water rectification, you need to come up with a chart like this. Now this is a small catchment. That's why you have only pipe A to H. You can have pipe 1 to pipe 1000, depending on how big it is. So having said that, we now look at the length of each pipe, we got the slope, and then the catchment area, the original catchment area. So catchment A is 15 hectares, catchment B is 5, catchment C is 14. If you look at it, you see that this is catchment A, 15, catchment B, smaller, 5, catchment C, catchment D, catchment E, catchment F, catchment G, and so on and so forth. So this catchment is emptying into this drain. This catchment is emptying into this drain. This catchment is emptying into this drain. Good. So after that, you've established this, okay? The next thing you do is you go to the catchment, you do what we call catchment characterization or catchment analysis. Catchment characterization or catchment analysis. Because you need to know the paved area and the unpaved area. And the paved area and the unpaved area will now give you the final peak runoff you need. Remember, our aim, our goal is CIA. So now we're looking for C. We're looking for C. A, we have it. So CIA, we're looking for C. What is the coefficient of runoff? Coefficient of runoff. Okay, that's what we're looking for. And for us to get the coefficient of runoff, it means we need to come and check what is the runoff coefficient of the different components of the estate. We have roads, we have gardens, we have this. We need to come up with one single final value to say, this is our working value. Okay, so with that working value, we'll now multiply it with our catchment area. It will now give us a new area called the effective area, right? We discussed it last week. It will give us, we are looking for the effective area. So, because it's not all the area that is contributing to runoff. It's not all the area that is contributing to runoff. So we want to know which area, and the area that is contributing runoff. When I say runoff, I'm talking about the one that is contributing water, the water that you want to take care of, the flow, is the one that is coming from the impervious area, the impervious side, because that impervious side is not allowing water to percolate. It's not allowing deep infiltration. It's not, so it is flowing on the surface. So that is the most critical area. That's why I keep saying it. Building your houses and flooring everywhere, you're not helping city management. It is not a sustainable urban design. You must make sure that the water that is coming from your catchment is not more than 50%. Because the drain, if all of us will empty our stormwater outside or on the public drain, then there will be flooding. So that's why you need to make provision for water to infiltrate within your own riparian catchment. So now, so you can see now, the catchment, we now go to the catchment. What is the representative of the catchment? Each catchment is made up of gardens, streets, roofs, and others. And we now go to our charts, which I Googled last week and I showed us. You go to your Google, get runoff coefficient of every catchment. It will give you 1,000 results. Garden and park have runoff coefficient of 0.1. What does it mean? Only 10%. When water flows in a garden, do you see water flowing on the streets of a garden? No, only 10%, because all of them will percolate, and you know why. Then streets. The number of streets in that catchment constitute 12% of the total catchment. Garden constitutes 63%. And the streets, because it's a paved street or it's a asphalted street, it has a runoff coefficient of 0.9. What does it mean again? It means that 90% of the water that falls on it flows into the drain, isn't it? So it does not allow, only 10% is lost coming from percolation, if there's ever anything like that anyway. For me, it's around 95% anyway. Then how about roof? Oh, roof is, that means the houses, total number of houses, shores, boils water, and what have you, in that catchment is only about 20%. And the runoff coefficient of roofs is 0.95. I've told us last week that you cannot get 100% because we expect that even rain, there will be a kind of small losses. Then others, we don't know what the others are. We just give them, they constitute 5%. So if you look at 63 plus 12 plus 20 plus 5, you should be getting something like 100%. So this is now, if you come to that catchment, out of the 100% of the catchment, these are the characterization, the characteristics of each of the sub-catchments. Now you get the average of this. If you get the average of this, you get it wrong. But what we'll get is what we call mean weighted average. There's a difference between mean weighted average and average, but I won't like to dwell much on it. Mean weighted average is a more representative average, because mean weighted average means I will say 1 times 6, this times 6, this times 6 divided by 100. So it will give me the weight. If you do the average of this, you might get 50%. But if you do the mean weighted average, you're going to get 37%. So the other parameters we are given for the catchment is that we're using a 10 minutes design storm. And we are told that it's a rural area. Take note, it's a rural area. Then, when we'll be designing the sewer, we are told that the population density is 100 capita per hectare. Everyone should understand this if you're in the first module. Then the water consumption, this one is when we come to sewer, that's all you need it. The water consumption is 130 liters per capita per day. The peak factor for water consumption is 2. You know what I mean. Parasite water is another layer of safety. The infiltration water is 0.1 for every hectare. Then we are using a pipe that has a roughness coefficient of 1.5. If you get it, 1.5. So all these are like takeoff, all the values you need to commence your design. The only one that I know that will confuse some of us that will not get used to is to find the mean weighted average. So sizing of diameter, which we've discussed before, sizing of your pipe depends on 3 factors. It depends on your discharge, the slope, and the roughness. We all know this one. Then your discharge is your wet weather flow. Remember, we have dry weather flow and we have wet weather flow. Wet weather flow is a maximum dry weather flow plus the storm flow. That one is self-explanatory. So if we are doing sewer, we have to determine what we call the dry weather flow. What is dry weather flow? It is that flow when there is no storm events. So we are talking about, that means we're talking about sewer flow. If you want to get your sewer flow, this is it. Your sewer flow will give you, it will be the water demand multiplied by the number of persons or the population density, multiplied by the factor of safety. Then you add infiltration water. Anybody that came for the first class, which is water reticulation, you should understand this formula. It's the same thing. So my discharge, when there is no rain event, is the water consumption per person, multiplied by number of persons, multiplied by a safety factor, and it will give me. This A6400 here, we all know is to convert it from day to seconds. So at the end of the day, my value that I'll be getting will be something like 0.401 liters per seconds per hectare. Why is it so? It is because we are dealing on the catchment scale level. They didn't tell us that we are designing for 1,000 people, 100 people, but they told us something. They said 100 capita per hectare. 100 capita per hectare. So this is what we call land use. So we are giving the land use. If you are designing for a virgin area, a place that has not been inhabited, the only thing that will help you is to estimate the land use. And why is the land use so low? Because it's a rural area. So it means for every hectare, you will meet 100 persons. For every 1 hectare, you meet 100 persons. So what is 1 hectare? 1 hectare is 1,000 square meters. One hectare is 10,000 square meter. So that means that's about 10 plots. If a plot is 1,000 square meter. So it means when they now say 100 persons per hectare, it means that for each plot, there are about 10 persons per plot. I just want you to get it from a layman's angle. So it means for every 1,000 square meters of land, you have like 10 persons living there. That is why when you go to do your design and you design a duplex, if the land development people, if the main control people did not see that this 1,000 square meters is going to house 10 people, they will not approve it. But as I said, this is for rural area. For urban area, it will be around 500. Yes, 500 capita a hectare. And if you divide it very well, it means for every 1,000 plot size of land, you need to design for 50 persons. Did you get it? You need to design for 50 persons. And you're talking about design for 50 persons, that translates to, for 500 square meters, it translates to 25 persons. Let me not go there. I just feel I should bring this into the level of a layman. I hope this is well understood. So 100 capita per day is because it's an rural area. Look at it, rural area. And their water consumption is still 130 because they are using German value. So, in Germany, you don't have rural areas, you don't have urban areas. It's like everywhere is just almost the same. People leave their villages in the morning, go to work in town. In the night, they go back to their villages. Unlike what we have here. You leave the poor people to live outskirts. The rich people stay inside town. In most European cities, is the opposite. Okay. And for the runoff, for the stormwater, sorry, this one is for the sewer. As I've gotten this value, all I now need to do is that if I go to any hectare, I'll multiply by this value. I'll get the discharge for that hectare. Right? Okay. For the stormwater, the maximum stormwater runoff will now be the rainfall intensity as a function of duration and frequency multiplied by the area impervious. If you break it down further, it will mean the rainfall intensity as a function of the duration, as a function of the frequency, multiplied by the total area of the subcatchment times the peak runoff. So what are these two? Multiply two of them together, we give you the area impervious. And the area impervious is our point of concern because that is the area that's contributing to runoff. Therefore, we now go and get the average of our peak runoff, which I told us we use weighted mean, what we call weighted mean. The weighted mean is that you multiply each of them by their corresponding area and then divide by the total area. The value will give you 0.371. If you go and do ordinary average, you might not get this. But in real life design, this 0.371 is assumed. As a designer, you can assume it and justify it. Somebody said, what is parasite water? Parasite water is another level of safety value. This is it has been proven that no matter how you do your sewer line, there will be waters that will enter inside it through infiltration. And parasite water can also be that if you're taking water from water board, sometimes when you're coming home, you go and buy pure water, you go and buy water. Okay. Now, if you want to estimate your sewer or your discharge or your sewage, I will simply use the value of water that water board is giving you because garbage in is garbage out. What you consume is what you produce. But then I need to factor in that sometimes you buy extra water outside what you're getting from the water board or from long distance water supply. So that can also be seen as water, as parasite water. Then sometimes it will rain. Some people will capture their rainwater and use it. So that one is not coming from public tap. It's coming from the one you captured. So that is also the parasite water. So as the word implies, the parasite is not captured, but it influences the queue. So I just wanted to take a look at this. You can see that this is rainfall value multiplied by the area of catchment will give you this. So for me to get this, I now have to take the average because I won't keep, I need the average to now start multiplying with every of the subcatchment. So the rainfall intensity, how do you determine the rainfall intensity? How do you choose your duration? How do you choose your frequency? We say that return frequency N depends on the risk associated with an overloading. So if you are in rural areas, you are designing for storm, 1 year return period is enough. If you are designing for surcharge, 2 years. If you are designing for flooding, 10 years. Nobody designed for flooding in rural areas because flooding will not cause any issue. For residential areas, you choose a design period of 2 years for ordinary storm. When we say design storm, that's what the one we will call drain, normal drain. You just want to design for normal drain. At any time, any day, the drain will just convey water out. Surcharge is if you are designing, you want to mitigate against surcharge. Surcharge is that the thing is now overflowing, like surcharging. You know what we mean by surcharge? That's extra flow. Okay, so you want to design against that. So you just increase your return period a little bit. But if you are designing it against flooding, you go for 20 years. City centers is a bit higher. Underground railways, return period is higher. Why is the return period higher for underground railway? Because underground railway should never be flooded. So if you are designing against it, you must upgrade. Imagine for the flooding is about 50 years. It means this 50 years simply is an indication that, look, on no account plus underground way. Because if underground subway rail station is flooded, it is the highest disaster of the highest order. I don't know how many of us have ever been to a place like Paris. If you go to Paris, you see layers of train. Like you can go 30 meters, 50 meters down to board a train. The whole underground of Paris is train. You won't see any train on top of Paris except tram. All of them are underneath. So as you're walking in Paris, trains are moving inside, down. So they will design it such a way that, because if it floods, it's death. Nobody will decide. UK, thank you, sir. New York, okay. New York, this was, should I say New York tunnels were recently flooded. That is what they never wanted. If they tell you how much the insurance company are going to pay. So insurance companies are willing to pay anything. So if you ask when this thing happened last, it could be more than 50 years ago. So they must have done everything possible to make sure it's not flooded. But unfortunately, climate change is real. It's real. And not just climate change. New York City is being built up. Like, where do you want the rain to go? Because everywhere is paved. Madison's, where? I mean, if you've been to New York, I've not been to New York. But you know, you can imagine in movies, you can't see grass, you can't see green anywhere. So when the rain comes, it's looking for how to escape. That's by the way. Okay. All right. So after then, you have done that. So for new systems, so this is what we use here. So for rural areas, we're going to use 1. Okay. And so on. Oh, okay. Someone has a question. What do you want to ask?
Yeah, Uche, well done.
Well done.
Yeah. Yes, you were talking about design, what's it called? Types. We have, you can design for normal storm, then you can design for flooding. So when will you know the time to design for flooding? Is it as a result of what's it called previous occurrences? Yes. Or you can just design, okay, I want this drain system to be taking care of my flooding or normal storm. So how do you differentiate when to design for normal storm and flooding?
Thank you. Number 1, thank you, sir. As you said, designing for flooding is something you do based on the risk associated with that development. If you are designing for an estate where each of the houses cost 500 million, I will advise you design against flooding, because if the estate will flood, the 500 million will become 200 million. Okay. And again, the work to design for, it also depends on your client. Your client has a say because it's your client that will fund it. Now, one thing about this design for flooding is that if you design for storm, normal storm, you can get a diameter of 600 millimeter. The same design, if you design against flooding, you might be getting 1 meter. You can see the difference. So by the time you do your bill and your costing, one engineer will be getting 1 billion. You that design against flooding will be getting 3 billion. Your client will not give you the work. So the design for flooding is associated with risk. And that risk is the risk of what will happen if this place is flooded. Like rural areas, we don't design for flooding in rural areas because if there's flood, if ever there's flood, it's farmland. Some crops will just die. I mean, next season will start again. So there's no risk. So I won't, because of I want to protect normal crops like maize and mango, whatever. I'll go and start spending 3 billion as against spending 1 billion. So you can see, sometimes we say it's a political decision. So, but all of them is embedded in risk. And you, the designer, should know the level of risk associated with this design. Like, for instance, one of the last design I did was for an outskirt of Abuja called Gidamango, around Karishi. Okay, so I told the person that brought my organ that brought it, I said, what value should we use for our, what do you call it again? For our prestation. I gave him 2 values, 120 and 140. He said, let us use the highest.
Rainfall intensity.
Rainfall intensity. He said, let's use the highest. And I asked him again, I said, what value do we use for our peak runoff? What do we use as our peak runoff? He said we should use 0.8. I said, okay, 0.8 is too much. I said, let's use 0.6. I think we'll let us settle for 0.7. So why do you use 0.8? He said, let's design for 50 years. That's what he told me for the peak runoff. Listen to this. He said, you know that all these outskirts, they are not well regulated. When they start building houses, all of them will use interlock. All of them will use, they will flood everywhere. So I was able to persuade him to use a lesser, I think we finally use 0.6, I think. Because by the time we started using 0.7 as peak runoff, meaning that 70% of what the flood will come to the drain. We found out that the drain sizes were so big, so huge, that when I drew his attention to it, it came down to 0.6. But for today, we're using 0.37 because this is a rural area. And so that area might be a rural area today, but the way Abuja is expanding, in the next 20 years, that place will become a semi-urban area. And then that design will still work. The idea is for your design to work as long as possible. So for your design to be able to accommodate every possible externalities, every possible change in land use based on human activity. So don't go and design something that after 5 years, the whole thing will collapse. Like some contractors will do on our roads. Roads are supposed to last for 25 years. After 2 years, the roads will collapse. It doesn't make sense. Okay.
Thank you.
Now, thank you, sir. So now you can see that this is the same IDF. It looks like the one Engineer Walo got. But whether you do it inverted or you do it straightforward, it is the same thing. You get the same value. Okay? It's just a question of how you want your chart. You know, some charts are up and upside down. Some are, so if you turn this one upside down, it will look like the one you have in your chart. Okay. So stormwater again, as we said, is your rainfall intensity multiplied by the impervious area. Impervious area, I can't help but emphasize this. It is not every rain that falls on the catchment that contributes to runoff. It is the impervious area, because impervious area, as the word implies, is impervious to water. So you read it off from here. So when you read it off from this design, you know, this is like a case study. Remember this again. When you read it off, you will get a certain value. Okay. Then also know that runoff has influence, slope has influence on runoff. So based on German guideline, based on one of their code and standard, DVR 118, if the slope is less than 1% slope and the degree of paving is less than 50%, it recommends you to use 15 minutes rain. If the slope is still less than 1%, in other words, the place is not too slopey, and the level of paving is greater than 50%, you should use 10 minutes rain. If the slope of the catchment is between 1% and 4%, you should simply use a 10 minutes rain. If the slope is greater than 4% and the paving is less than 50%, use 10 minutes. If the degree of paving is greater than 50%, use 5 minutes. But let me advise you, just use 10 minutes. for your real life practical design. You can see that 15 minutes and 5 minutes are on the A stream. So use the one that is commonest, which is 10 minutes. 10 minutes is the same thing as 600 seconds. You're going to meet it somewhere, so you don't get confused. So this is a guide. You know, if you remember how we do design, there are guides, there are parameters to use, but there are guidelines. How do you determine those parameters? Like we just did now. Okay, how do you know whether you to use a 1 year, 2 years, or 5 years rain? So this is like a guide, also based on code and standard. And that's what we're fighting for us to have code and standard in NSC. But that's by the way. So you can see that these 2 slides is just to give you a guide. And after you have guided, we'll now go to the redesign. So if you go through that chart, for a rain of 10 minutes and for 1 year, is that not what we're doing? We're doing for 10 minutes and 1 year. It's giving us 126 liters per second per hectare. Don't ask me why I am doing it per hectare. Because at the end of the day, I will just be multiplying by hectare, and what we want to get is liter per second. But we're getting it per hectare because we're getting the unit value flowing in every hectare. So it means for every 1 hectare, the amount of rainfall that is coming out is 126 liters per second. So every second, we're having 126 liters. This thing will serve as a guide, because the next thing, you're going to get your Q, you get your charts, and then you start to calibrate. Any question? Then flow time is T. If the flow time is longer than 10 minutes, it's the only part of the catchment produces runoff. Largest discharge occur when rain duration equals flow time. That is why I was telling us about flow time, rain duration. All this is to justify why you should use 10 minutes. And why, if the rain is coming from a distance, that it will take you more than 10 minutes to flow into the drain, then there's small error, or it will not give you the real discharge. The real discharge will come at 10 minutes. I'm trying to demystify this because many people get confused about this, but in a simple way, just use 10 minutes. And let's close the matter. So when the duration is equal to the time of flow, that is when the whole catchment is contributing to runoff. Flow time depends on velocity. However, velocity is unknown. So here, we normally assume a velocity of 2 meters per second. 2 meters per second is an assumption. So this is it. We are moving to the design now. If you're going to design, the first thing you do is you choose your frequency, choose your N. As a consultant, this is where you explain why you are choosing your N. You explain why N is what it is. Then you choose your estimated time of flow upstream. How long does it take the water to drop from where it drops to the time it flows into the drain? It should be 10 minutes. If it's less than 10 minutes, use 10 minutes. If it's more than 10 minutes, use 10 minutes. That's an assumption. Then the next thing, you consult your IDF. If you consult your IDF, since you know the frequency, you know the duration, then, and you know the city, of course, you can now read off your rainfall. Then that is for the storm. For the sewer, you calculate your wet weather flow. Wet weather flow will now be your maximum dry weather flow plus infiltration water. And that will give you wastewater flow, WW. That one you use it to design your sewer. Then after then, you now go and choose your pipe diameter while considering the security factor. However, you should remember that required diameter depends on the discharge, the slope, and the roughness. This should not be a big deal for those who have attended the last class. Engineering is engineering. So after then, you can also consult the table to get your real velocity, which we did, remember, last time. That same chart we use in water design. You can also use it here another chart based on different shapes of drain. Then later I will explain this. Degree of filling. Partly full, full. This is like a safety factor. Okay. When you do your design, the code and standard says that your pipe should be 70 to 90% full all the time. Okay, we discussed it in water reticulation. So that's what this slide is talking about. Okay, so from there, you compare your results, then you do iteration if possible. So for instance, this is catchment A. I wish I told us last week, we would have printed this thing out. Hold it in our hands so that we can all understand, be on the same page. I want everyone to open it. See catchment A, start, end. You number it. This is a calculation sheet. Look at the calculation, what the larger calculation sheet looks like. It looks like this. So this is what you're going to develop. This is what you're going to develop. But for you to develop this, you need to understand how each of them is computed. So that's what I'm going to show you in the next few minutes. We're going to go on break. Please, I want to take some water. We're going to observe 5 minutes. This is pipe A here. Where is it starting? Here. Where did it end? Here. What catchment is it encumbering or is it serving? Is 15.63. So the first thing we want to design is the wastewater, which is the sewer. Let's do the sewer first. After the sewer, we'll do the storm. So for the sewer, this is the catchment. Remember, when it comes to sewer, there's nothing like runoff. We're not dealing with runoff. Rather, we are dealing with wastewater flow. Here, dry weather flow, because we're designing our sewer. Our sewer is our foul sewer. So our interest is dry weather flow. When it's not raining, what quantity of wastewater is flowing there? So we said it is the consumption of one person multiplied by the number of persons, then multiply by the safety factor, and then you add infiltration water, which is just a negligible factor of safety. If you finish it, because our catchment is given to us in terms of land use, which is 100 capita per hectare. So hectare will still show up in our calculation. So this is 0.4 liters of sewage is flowing out into the central sewer every seconds per hectare. It makes perfect sense. So when you now come to this catchment that is 15 hectares, so if 0.401 is the value for 1 hectare, then for 15.3 hectares, it will be 0.401 multiplied by this 15 will give you 6.26. So this is now 6 liters of sewage is what is flowing out of a catchment of 15 hectares. That's what it means. Any question? For B, the starting point, the ending point, all the starting point and ending point are not relevant. It's just for you to get the slope, because the slope is a contributing factor to the size of your drain. If you have a huge slope, your drain size will be small. If you have a flat slope, your drain size will be big. So the size of catchment B, look at catchment B, is total times 5.47. If you multiply 5.47 by the catchment flow per hectare, the wastewater flow per hectare is 0.4 liters. It will give you 2.19 liters. Catchment C is the same thing. This summation, this accumulation is this. Catchment A or pipe A is conveying a flow of 6.26. When it comes to catchment B itself is conveying a flow of 2. Therefore, the accumulated flow at catchment B is now 6.26 plus 2.19. We've done this before, gentlemen and ladies. We've done it before. It's the same thing. It means at point B, the quantity of wastewater flow is now 8.46. So as wastewater is flowing downstream or it's flowing towards the treatment plant, it's aggregating, it's accumulating, it's getting bigger. And the pipe size will be getting bigger too. So this is exactly what we did in the last module for water reticulation. That as the flow is going downstream, it will be accumulating, to be getting bigger, to be increasing in size and numbers. And it's increasing in size and increasing in number, so the expected pipe size will be increasing. But when it comes to C remains the same. Why? Because C is an independent catchment. C is an offset catchment, it's an offset. So it's not in the main network. The main network or the critical part, let me use that word. The critical part is A, B, D, F, H. Yeah. So you can see that catchment C remains the same. Same here, same here. Catchment A is same here, because there are no previous catchments. This is just the beginning. This was storm. Don't worry. Let's finish sewer. So this is wastewater. These charts combined wastewater and stormwater. So, but I'll split it out for us. I will make it separate. Unless your client has asked you to do both the stormwater and sewer line. But if your clients have only asked you to do the sewer, wastewater, you stop here. If they ask you to do only the storm, it will be between here and here. Right? Good. Now, let's go. We have done this. We got this. Okay, now, catchment C will now be the area multiply 0.401. It will give you this. Catchment D, watch this now. This is the area of the catchment. Multiply by 0.4, it will give you 1.57. But the accumulated flow is now 15. Why? If you look at the position of catchment D will be B plus C plus itself. Catchment D again is B, which has already captured A, plus C, which is 8 plus 5 plus 1.457. That will give you 15.56. Why is it so? Catchment D is on the critical part, or is on the main pipe. So it will be B plus C plus its own contribution, because there are also houses here which are also throwing in wastewater into this pipe. Catchment E is 0.95. The accumulated flow is also 5.95. Why? You know why? Because catchment E does not have upstream. and it's not on the critical part. Catchment F is on the critical part. So catchment F will be the area of catchment F multiplied by the CR flow, which is 0.4101. It will give you 1.88. Then F will now be the value coming from D plus E plus itself. Give it 23. Value from D plus E plus F. Value from D, from E, from itself. Now, why did you see F being two Fs? The value, why you see 2F is that if you look at F, there are two ways you can access F. If you can access F like this, or it can also be E plus F. Okay, so but the bigger one takes precedence. Let me not confuse us with that. So you go to G. G, the catchment of G is 14. You multiply by 0.401, it will give you 5. The accumulation will be what? Still 5. Why? Because G is not on the critical part. Then when you come to H, H will now be, the area of H is very small, 0.94, 2.22 hectares. Multiply by 0.4, it will give you 0.94. Therefore, H will now be what? F plus G plus itself. F plus G plus itself to give you the final value. Any question? So that is the wastewater flow. So if you now come here, you now do what we did last time in our water reticulation. So for this one, let's assume I'm using a circular pipe, which of course is what I should use. It's pipe A. What's the size of pipe A? Pipe A is 6.26. I will now go to I will introduce us to new charts soon. But let's first maintain our water reticulation chart because this is an underground thing, so it will work. Circular pipe, underground will work, PVC pipe. Are you with me? Go to our charts. There is it. Okay. If you can't find it, you just go to water reticulation chart, the same chart, just monogram. We have it? Sure, we do. So let me use PVC pipe, for instance. So this is the PVC pipe. (6.26) is the flow for pipe A. So this is 6. What slope do we use again? The slope is there, but the slope is about 3%, I think, about 3%, because 0.3, 1/200 or thereabout. So 6 against 3 is giving me 125 mm. So the answer to pipe A is 125. But the law says anything less than 150 mm pipe, you should use a 150 mm pipe. Remember, we also did it in water regulation. Anything less than 50 mm, use 50 mm. So, but in this case now, anything less than 150, you should use 150. So this one will go 125, but we're going to use 150 because if you say 125 is not in the market, 125 is 5 inches. I don't think you can see 5 inches in the market. But the law, the code supervises every other thing. So for pipe B is 8.46. So I'll go to my monogram and go to 8.46. So let me simply go to 8.46. I don't know what the slope is, but the slope is around same 3. This one is giving me 150. So pipe B is 150 mm diameter. The velocity, I can also read it off, of course. The velocity is 0.7. The velocity is 0.7 at that point. So we'll go to the next one. If I come to pipe C, I cannot do pipe C. Pipe C is giving me 5.564. I've already done a 1 for 6 points, so I'll quickly use that one. So it's 150. Are you with me? Pipe C is less than pipe A. So, but because I have designed for pipe A already, and it gave me 125, which is designed, provided is 150, I'll just use the same value for 150. But when it comes to pipe D is 15. So I have to design it. So this is 15 here. 15 against 3. It's giving me about 200 diameter pipe. Something close to 175. So it's either use 175 or use 200, but I will advise you to use the worst case, unless it's too worse. I hope our silence is a testament, an indication that we are following, we are getting it. When I come to pipe E, I'm not doing any design because I have done a similar design for pipe C, which I also did for pipe A. So I'll just put the value there. Then when you come to pipe F, I have 23. So I need to design it. So 23 is somewhere here against 3. It's still giving me 200, but on the lower side. And the velocity is about 0.8. Finally, the biggest one is 30 liters per hectare, which is at the tail end. That is, in real life, that will be the wastewater treatment plant, at the point of wastewater treatment plant. And this is 30 here. So 30 against this is giving me around 225, not up to 250, but I can use 250. So I'll pause the recording. So for the storm, this is the rainfall multiplied by the area of impervious, which is the same thing as rainfall multiplied by the catchment area multiplied by the peak runoff coefficient. So if you multiply these two, you still come back to this. So if you go to your IDF and read off, just like I read off not one line ago, you will get the 126. So let's go to IDF. So let's assume we're using worry. We're using worry. And using worry, we're using 1 year. Remember, we were saying rural area. We're assuming that worry is a rural area, even though worry is not a rural area. But let's say worry is a rural area. So for 10 minutes rate, this is my 10 minutes. I'll go up. I'll go up. So where you have 1. So here is 126. Did you see it? 126. So this 126 is now your rain. Why we are just your focus is to get one rainfall data, just one, because it is only one, and that is be the worst case. So what is the amount of precipitation in this area? Because you are designing the sewer. I have sent this sheet, this calculation sheet. I have sent it, sir. It's in the chart. unless you log in late. But after now, I can send it again. There's no problem. Every material you see me use, it is your property, your page. In fact, it's in our cloud folder right now. I'll put it in the cloud folder. Okay. So you can see that 126 is what is coming out per hectare. So here, we're using 10 minutes. We're using frequency of 2, but let me change it to 1. Oh, I can't change it. This is PDF. But just assume that this place is 1 year. Assuming we are doing we are following our terms of reference. Okay. Then the peak runoff. Let's assume that worry is also this. We assume this thing we did. You can assume it. But I've also shown you how to get it theoretically. Theoretically, to get it theoretically is this. This is it. What is the green area? 63%. What is the street? Asphalt street. What is the roof area? What is the others? These are the different coefficients. If you take the mean weighted average of this, you get 0.37. So you now multiply the area. So the formula now, as we know, runoff is the same thing as flow. Q is the same thing as runoff. Runoff is the same thing as Q, represented by as QR. Is R times A times the peak runoff. So the peak runoff now means 15.63 multiplied by 0.37. That will give you 5.82 A0. This 5.80 is now the effective impervious area. So from 15.63, the area that is contributing to rain, or the area that is paved, or the area that is permeable to water, is only 5.8. And that is the critical area. That is the area we need. So I will now multiply this area by the rainfall intensity, and I will get 732. When I get my 732, I'll now go to my chart. I'll read 732 against 5%. And it will give me, let's read it. 732 is almost like 700. Somewhere here, look at 700 now. See it here, 700. I'll read it against 5%. It's giving me something about 600 millimeter drain. 600 millimeter drain. So for catchment A, okay. All this is an exception, please. This is not like a mistake. This thing is for storm. So I will now go to the one for storm. I think I've shared both of them. This is it for storm. Good. This is for storm. So stay with me. I look at it. The same thing I saw there. So this is the one I should have opened. So for storm now, I'll do this. From table, it's giving me 700 mm. So you can see the big difference between sewer pipe. That's why for sewer pipe, we are using PVC. But for storm, we'll be using concrete pipe or big pipe, fat concrete pipe most of the time. Concrete pipe. So 700 mm pipe is what we need. For catchment B, this is the area, the original area of the catchment, multiplied by the peak runoff coefficient, the effective runoff. The effective area is now 2.08. Multiply 2.08 by the rainfall intensity, it will give you this. However, B will now be this plus the one coming from A. So the total area will now be 9.88. Total flow will now be 9.88 liters per second. Therefore, if I read it against 3%, which is the slope of the pipe, it will give me 900 mm. I expected this one to confuse somebody, but any question? Catchment A, catchment B. Look at catchment B. Catchment B has upstream. So the total flow at B will now be the value upstream plus the value downstream. Catchment C will not have that thing. Will not have upstream. Look at it. Catchment C, the original area is 14 hectares. Multiply by the coefficient to give you effective area of 5.22. Effective area of 5.22 multiply by the storm or rainfall intensity, sorry, it will give you 6.58. So if you look at 6.58, it will give you 800 mm. Are you there? Catchment D. After calculating catchment D, the effective area, the total area is 3.91. But when you multiply by the runoff coefficient, which is an indication of the degree of paving, to give you 182. However, the flow at D is not 182. Rather, it will be the flow from the previous catchment, which is C plus B plus itself. And that will give you 1486. And the slope is 0.25. So if you read 0.25 against 2.5, you're going to get 1.1 millimeter size pipe. Catchment E will not have such. Catchment E will just be itself because it does not have upstream. So it will be 695. And we have done something close to 694 before. So we simply write 800 mm drain. But remember, this 800 mm is for the circular drain, pipe drain. If it's a trapezoidal L, V, or U channel, there's a different chart to use. You cannot use this same chart, right? Unless we get value, we now go and decide to know what size we convey it. So we'll go to the big one. Catchment F will now be itself plus the previous ones plus this one to give you this, giving me 1,200. So you can see it. Catchment G is just itself. Once you get this value, automatically know it's as 800 mm. So, and so on and so forth. So this is how you do, and you now size the whole pipe. When you size the whole pipe, you now go and detail it in your AutoCAD. You put the pipe, put the shape, put everything. So for instance now, next week, we're going to dissect this. So for this week, I would like us to read this rational method, this chapter rational method, read it from the beginning to the end, so that by next week, we'll now put it into this table and show you how this table is gotten. And this is the calculations table. Very difficult, very complicated, but from what I have taught you today, I have no doubt in my mind that you get it perfect. You just get it perfect. So this is question time. The next 7 minutes, I expect you to ask questions. And I think we have quite a huge number of people in the class today. Anybody joining us for the first time, apart from Rufus, I think?
Yes, good morning.
Yeah, well done.
Yeah, it's Engineer Douglas.
Okay, well done.
For the first time.
Okay, so I think you're running the platform and just try and get all the screen, all the recording. And just
yes, I'll do that. I've gotten it already, and even this, I think I'll be expecting it. Somebody wrote on the group on the chat if you can get the chart you are using for this illustration, so that on our own.
Okay, let me see. Yeah. Okay, you're not in the water. So everybody has it already, but let me upload it again. It didn't come for, you are not around for the water stuff. So I'm uploading the chart now. But no, I always say this: if you go online, This is another chart. Let me give you another chart that I got from Federal Highway Manual. I have uploaded it. But it means you have, but now that chart now you need to sit down and learn how to use it. See, any chart you take online, there might be need for you to sit down and know how to use it and learn how to use it. You need to know the laws. It's like a psychometric chart. If not, somebody not explain psychometric chart to you, nothing will make you understand how to use it. So here we go.
Hello?
Yes?
Yes, I want to ask, is there a dedicated a chart peculiar to Nigeria, or is just maybe any uploaded chart that's related to this area that one can use? That's my question.
Well, you say if there's any chart dedicated to Abuja?
No, I mean Nigeria standard as it is.
For IDF chart?
No, all these charts you are using, say if we download, we can go online, you know, and
No, brother,
so
unless you be the first to do it, sir.
Okay.
We've not gotten to that level where we do things and put it online.
Okay.
The thing is in someone's laptop now. And the person is hiding keeping it close to his chest. But thank God for Google. Google have demystified everything, everybody and everything.
I'm going to ask others, comments.
We're not hearing you, sir.
Sorry. Just like my last friend that said something about we using anything and all those. I think
no, it's a template. We are trying to template.
Yeah.
Chart. What I mean, chart is a template. You know, as a consultant, you can. I've seen many consultants in this country. They develop charts for themselves.
Uche, sorry, I know you are German trained and you are used to German standards. But Nigeria will always tell you that, oh, we are doing British standards as a parent guide. So I'm just thinking, is there I mean, normally if you're designing for, say, Korean or something, would they just accept somebody can just go and use American standards, someone can use Indian standards, someone can use German standard? Will nobody ever say no?
We are leaning towards British, sir.
Eurocodes and all those, and
yes, thank you. And which is, you know, in my last class, I've said this before. All this code, in fact, we all agree that our aim here is to learn the first principle. The other one is the technical issue. But notwithstanding, the different standard, there's no much difference. In fact, if I go to Canada tomorrow, and they will tell me that their rainfall in Quebec is 130. I'm just going to move my Nigeria 120 and replace it 130. Are you getting me? Yeah. It's only that in the case of Nigeria, we have to get it is difficult, but as I said, 2013, the Minister of Works, together with Korean and Minister of Works, they came up with this information that I gave us. It's called the Highway Design Manual. We've been hoping that NNC and Korean will do for the other sectors, but so far we have been lazy about it because we have British code.
Let them finish collecting dues first.
So that's the thing. We've been lousy. And I didn't want to talk. Last time they've been talking about code and standard, and I saw one of the officers calling people to bring any code and standard that they have. And I was like, if I talk now, they will start talking. If I talk, they say, some people just see as being stubborn or you are showing off. You don't ask people to bring any standard that they have. You must localize it. You must say who have developed, because everything about code and standard, no country even start from scratch. You leverage. Even America took the British and the French. Not even the French. They took the British, they modified it, and they call it their own. Even current president have said that all we need to do is to adopt. Find a country, adopt it. If there's a place they are putting snow value, I'll remove it. I don't have snow. Okay? If they are putting their rainfall intensity at 8, I know my own in Lagos is 140. I know even my own in Maiduguri is around 180. It's around 80, 90. Mina is 120. Lokoja is 130. You know, all that kind of thing. Okay, but so far, I think our method is use a standard, justify it. If you're using British standard, tell us why you're using British standard. And maybe make a reference that I'll be using this standard. But this other standard says this, and they are the same. So I'm picking the value. I don't know if it makes sense.
Yeah, you're making sense.
Now watch this. Rational method chart. You see what I'll see. Rational method. Chart. Let me even put in Excel. See, Google has given me option. As oh no, no ratio. I say rational method. Sorry. Now look at it. If you spend the next 2 minutes going through some of these sites, you're going to download. Okay, look at them. Look at this person will produce a program on it. But I suspect if you go to download this one, this person will ask you to pay. This rational method is somebody who is smart, but he will pay. Okay. If I didn't get what I'm having, I'll come here and I'll change it to rational. I'll write it rational method templates. But if you can duplicate, translate the one I have, as in clone it, I mean, you can do that. I actually have one. Let me show us one I have, but let me show us one I have to tell you it's not a big deal. Watch me. Good. I'll show you one I have. Excel. Okay, Storm Network. Did you see that? I developed this myself. But unfortunately, I'm not going to share it now because I would like you to develop one. I gave it to as assignment last week, even during water. I thought this is no big deal. So this is it. So this is my coefficient, 0.8. This is my effective area. When I multiply the area by 0.8 to give me this. Rainfall duration I used was 15 minutes. The rainfall intensity is 140. Then the discharge in cubic meter is 163, 178, and so on and so forth. Then I use a reducing factor. Oh, no, increasing factor, sorry. I added another factor of safety to take care of, because this thing was about 300 hectares. So this is now what somebody called modified rationale. Did you say it? Okay. So, but I'm interested in seeing who will get me one that is better than this one, because this one is just it doesn't have it's just too common. It's too common, but I know that online you're going to get some wonderful ones, some beautiful ones, and it could just be better. Look at this one. If you look at this one is going to be better. Control charts, how to, right? You will get something beautiful. Image, news. Okay, in Excel, I think I'm making a big mistake. If you see this chart, I'll just put X, L, XX, right? No. Next slide is the white card. Yeah. I'll get a lot of it.